In this section, we'll talk about viewing attributes and capabilities. And a key part of viewing is cameras and lights. We'll talk about some supplemental viewing tools such as the Axis Triad nav cubes that are supported out of box and are configurable. We'll get into a little bit of how we can use sub-windows to help enhance our view display, and talk about the various coordinate systems in Hoops Visualize and how it's important to know how to convert between them depending on incoming information from user interaction. So this has been touched on earlier, but to review in a little more detail, cameras will determine the current view of the scene. So for each windowed segment, so we could have a window key or a canvas. If we're using the view hierarchy, we have the canvas, view, and model, but the canvas would be at the same level as a windowed segment. The amount of the scene underneath that window key or canvas that is viewable by the current camera or cameras, there can be more than one camera, will get mapped into that window. So the camera determines what I see. Each segment has a default camera, just like any attribute. You could review what those camera properties are, the specifics are, and here's the different aspects of a property. It's similar to a real world camera. I have my position, my camera, its target, a field, what the orientation is based on up vector, and then a different projection type, for example, perspective or orthographic. This section, the programming guide, will talk about all the different ways of setting up the camera. And here's a code snippet that shows us setting each component, each property of the camera. Set camera, as we can see, is going to be one way of modifying it, but we can then also do a camera kit here. And so that's, as a transactional object, we set up a camera kit, and then we set our camera using the kit rather than directly setting each one of those properties directly with a database call. We want to emphasize our camera setup guidelines. So this is important to ensure that there is an adequate amount of Z buffer resolution for my current scene. And we recommend that this kind of golden ratio. The distance from the camera position to target should be about 2.5 times the field width. So this does maximize that Z buffer resolution and ensures that as many buckets of the Z range are mapped and or allocated to the geometry mostly centered around the camera target. So for example, if I had a very, very narrow type of camera, very narrow field, and my position and the distance between my camera position and camera target was extremely far, and this ratio was 1,000 to 1, I'd have a very, very long range for my Z mapping. And what can happen then is if I have, especially situations where I have both faces and edges being visible, even though we try to float the edges a little bit in front of their corresponding faces, or actually what Hoops Visualize does internally is it displaces the faces into the screen or into the Z buffer a little bit so that the associated edges will sit on top. If we don't have adequate Z buffer resolution, you'll see something called edge stitching. So you'll see those edges and their coincident faces. The edges will kind of stitch in and out of those faces. So many times when there's kind of camera issues or edge stitching or common faces that are nearly coplanar but still not the same value, and they start bleeding through each other, it's because your camera might not be set up properly. So it's important that if you have operations for zooming the camera, real-time zooming in and out of the scene, that you maintain this ratio. In this case, we wouldn't just want to change the field, we actually want to move the camera forward and backwards to maintain this ratio. There are two different kinds of lights. A distant light is basically a light where, similar to the sun, where for all intents and purposes the rays are coming in from an infinite, something that's infinitely far away. So all the rays are parallel to each other, and that gives a good general lighting to the scene. Whereas a spotlight is going to have kind of like a table lamp or a desk lamp is going to have, it's going to be a directional light. And it will have a light cone with a certain amount of fall off, and it's directional. Lights are a bit special in that the scope of a light is its entire containing window. So if I have a windowed segment or a canvas and I have many subsegments down the tree, if I have a light or lights way down in a nested subsegment, that light will affect everything in that whole segment tree all the way up to the first containing window. So they're a bit unique in that way. Now, there is individual control. I can set attributes to say whether lights affect edges or faces or vertices. And so I do have control over the sub aspects of geometry that are affected by lights. A couple examples of the methods for inserting lights. Here's one example. If I have a spotlight, a key to a spotlight, I can set camera relative true. So that means it will be respond to the camera. That's again an omnidirectional light source. Okay. Some other view and navigation aids. We support out of box both an axis triad, which shows the current orientation of the view or essentially of the camera, and there's a navigation cube that's also available that's interactive. So the navigation cube can be picked on at a corner or in the middle of a face, or directly clicked and dragged to change the camera orientation. If you run the Hoops demo viewer, you will be able to see these in action and experiment with them. These are supported on the view class, as we show here. We can get our axis control from our view object, and also our navigation control, and control the location and the size. Again, the view class is part of the canvas view model hierarchy. So these are only available if you're using that convenience view hierarchy. As mentioned previously, when we have a windowed segment or a canvas, Hoops Visualize internally is actually creating its own concept of a Hoops window, a software abstraction of a window. It has nothing to do with a window that's physically on the screen created by a native GUI toolkit. But Hoops has that concept of a window. We will, again, in review, we'll take the contents of the whole scene graph underneath a windowed segment or a canvas that is viewable by the camera, and that's what will be drawn into the corresponding native GUI window, the actual MFC, WPF, Qt, etc. Window on the screen. Hoops does support setting actual Hoops software abstraction windows down through the scene graph. They're an attribute of a segment, and they can be applicable for use as overlapped fixed screen space items. So both the Axis Triad and NavCube are internally implemented by using windows, so they stay fixed. Sub-windows are always going to be drawn on top of their parent windows. The window frame or border can be set to be visible or not. The window can have a patterned background, a solid background. You can set the color or the pattern. Okay. So if we look at 3.4a, we have an example here where we're specifically setting a sub-window. We can set up a sub-window kit, set up its properties, has a rectangle, defines its size, and we create a subsegment, and we have a sub-window. Okay. We're mentioning here in a very important note, all visualized windows have an implicit standard window that's the size of the main window. So I've mentioned that already. Jumping ahead a little bit right now, when we talk about window coordinates, the bottom left corner is -1, -1 in Hoop's window coordinate space. Top right is +1, +1 in X and Y. So window coordinates are 2D coordinates. This will become useful for us when we deal with selection events and interacting with the scene.